Hi everybody. What if your dependent variable is binary? So what if you have this relationship between x and y, where y can take on a value from two different values or events? Okay, so then in this case y can only take on the value 1 or 0, right? Depending on the x value. In this case, you can actually use the regression framework to create a y hat, the expected value of y given the value of x. So and often we say that this is a linear probability model because you can think of the 1 as 100%, right? And 0 as 0%. So you can think of these outcomes as probabilities. And one example could be that you're looking at companies who have gone bankrupt. They are in default. That would be the 1, and if they survive, then it's a 0, right? And then you try to explain bankruptcy by modeling this equation or modeling this process by looking at several different metrics. So we have the linear probability model, but we also have the probit and logit models to estimate probabilities. And the probit and logit models, they are nonlinear models, and they are somewhat more complex, especially when you deal with the explanation of changes in the x compared to changes in the y. So that's why the linear probability model is a very good place to start. So what if you have this linear probability model, which is given by the binary dependent variable y, and the rest is, as you have seen before, just linear combinations of x values, right? So this linear model actually gives you the probability that y equals 1. So if you look at a specific x, then you can just feed that into the equation, and then you get a probability that y equals 1. Okay, so here you might have 0.59, for example, 59%. So this is the intuition behind it, but why is it that the linear probability model actually gives us the probability that y equals to 1? Consider this. You have this linear probability model with two independent variables, x1 and x2, and by the first least squares assumption, you know that the expectation of y given values of x, this is both x1 and x2, right? It's equal to a linear function of x1 and x2. And because the y is a binary variable, we know that the expectation of y, given the values of x1 and x2, equals the value of y in the case that y equals 1 times times the probability of y equals 1 given the values of x, plus the value of y in the other event, times the probability of that event, right? So to get the expected value of anything, you just take the value at each event times the probability at each event, right? So if you're throwing a die, you have values of 1, 2, 3, 4, 5, and 6, and then you just times the probability of getting a 1 times the probability of getting a 2, and so on. And then you just add these numbers up to get the sum, right? So that's kind of a quick repetition, and because in the event that the value of y equals 0, the product between 0 and the probability of getting 0 is just 0, so we can disregard that, which leaves us with the expected value of y given the value of the x variables is just the probability of getting a y equals 1. And just look here that this expectation of y given x equals something, equals this, right? And the same expectation of y given the values of x equals this, which means that these two have to be equal to each other, right? So we can put them together, and we find that the probability of getting a y equals 1 equals this linear combination in our regression. So now you have proven that the value in this regression, the right hand side of the regression, actually gives you the probability of getting a 1. So which means that you can perform this quite simple regression and get get the coefficients, and these coefficients you can use by inputting new data to get the probability of new instances. For example, you're looking at a brand new company and you wonder within the next year, what is the probability of this company going bankrupt? So the estimation method is just the ordinary least squares, in which we vary the coefficients, the slopes and the intercept, in order to minimize the sum of the residuals. And this just means that you minimize the distance between the regression line, you just minimize the distance between the regression line, for example here, and here you have the regressions, or the residuals. Okay, so it's the same method as in the previous videos, so you're quite familiar with that method. So how does it actually work? We can look at the exercise 7.1 from worksheet 2, and we are in this case interested in investigating the determinants of women's labor force participation. So our dependent variable is in the labor force, which is a binary variable, because you can't be in the labor force and outside of the labor force, and you can't be in the middle. Okay, in this case. Okay, so it's equal to 1 if the woman reports working for a wage outside the home at some point during the year, and 0 otherwise. And the independent variables, the x variables, are education, the number of years of education, kids lower than the age of 6 years old, less than 6 years old. And by these two independent variables, we are trying to figure out the probability that a woman is participating in the labor force. So we have this regression, and this is the beta 0 hat, the estimated intercept, and then we have the slopes here. So, and what does these slopes actually mean? So, what is the predicted probability of labor force participation for a woman who has 12 years of education and two children under the age of 6 years old? And what about 3 children under the age of 6 years old? So, to get the predicted probability, we just input the information that we get is that we have education equals 12. The woman has 12 years of education, and 2 kids less than 6 years old. So then we just plug into the regression, and we get 0.156, which means that this is the same as 15.6%. And if a woman has 12 years of education and 2 children under the age of 6, then we predict that the probability of labor force participation is 15.6%. Okay, what if the kids, or what if she has 3 kids lower than or less than 6 years old? Then we just plug into the equation, and we get a number of negative 0.068. This is negative, and you know that probability is a number between 0 and 1, okay, which is just which is equal to 0% to 100%, right? It's the same, which means that our model gives us a negative probability, which is impossible. And this is one of the downsides of getting the downsides of using this model. It might give you a probability lower than 0 and a probability above 1. Okay, so what you do when you get this nonsensical result is that you truncate the range of numbers, which means that instead of having this y hat, which can be higher than 1 and lower than 0, you just move these negative numbers up to this 0 probability, and you move these probabilities who have a number or a value above 1, you just move them down to 1. In this case, you get a probability function which looks like this. Okay. What is the coefficient on education actually telling us? Okay. We look at the probability of getting a y value of 1, right? Which means that if you change education by 1, holding everything else constant, then you get the change in probability of getting y equals to 1, which means you get the change in probability of the woman participating in the labor force. And you saw that this, if we go back to our coefficient on education, it's 0.046, which is 4.6%, right? Which is a 4.6% increase. So what does that mean? It means that if you change education by one extra year of education, the probability of a woman participating in the labor force increases by 4.6%. Okay. And for a woman with 16 years of education, what is the predicted change in probability of labor force participation when going from 0 to 1 young child? Okay, and from 1 young child to 2. And this is quite easy because the change from 0 to 1 child is 1. The change from 1 child to 2 children is also 1. And because we have a linear model, then the change in the predicted probability is just the coefficient itself, which means, and it's negative 0.224, which means that if you increase the number of children by 1, you decrease the predicted probability of being in the labor force by 22.4%. Okay, so what is the advantage of the linear probability model? Well, the main advantage is that it's super easy to estimate, because it's just a ordinary multiple linear regression. And the coefficients are super easy to understand. If you just change the x value by 1 unit, then you change the probability with the same amount as the value of the coefficient, the slope. So it's super easy to understand. However, one of the main disadvantages is the probabilities can be greater than 1 or less than 0. So, what about statistical inference? Confidence intervals, t-test and f-test, they can be used, okay? But you have to remember that the linear probability model always produce heteroscedastic residuals, as we saw in the example above. The fitted line is as such, right? Whereas the data is either at y equals 1 and y equals 0, which means that you have high, large, or the size and the expectation of the residuals is varying based on which value of x you are looking at, right? So close to these intersection points, the expected residual is 0, whereas away from these, if you just go away from these, the expected residual will either be negative or positive, right? So always use robust standard errors, right? So we saw the intuition behind why the residuals are heteroscedastic, but to show this in a more mathematical sense, we can look at a simple regression model where we only have for example 1x, and y is a binary variable, so it's a linear probability model. Then you can say that the variance of the residual given the value of x equals to the variance of y given the value of x, and what is the variance of y? It's just the probability of y equals to 1 given x times the probability of y equals to 0, but the probability of y equals to 0 is just 1 minus the probability of y equals to 1, right? Which gives you this probability of y equals to 1 is just the linear model itself, which we saw some slides ago, times 1 minus this probability. And here you see that you get a squared term, and you get this linear term for x, which means that the residual is not constant over the values of x. So, and lastly, the measures of fit, we have learned that we could use the r squared or adjusted r squared to measure the fit of a model. But in this case, the r squared is not very useful because we can get these nonsensical values, and if you look at the r squared, the definition is the explained sum of squares divided by the total sum of squares, and here you see that with the linear probability model we can get nonsensical fitted values of y hat, right, above 1 and below 0, which means that when the dependent variable is binary, it's possible to have r squared equals to 1, even though the data points are not exactly on the line. So that was the linear probability model. See you next time.